To understand why dark energy is so important to the emptiness of the universe, it helps to revisit a basic idea that feels intuitive but turns out to be misleading. We tend to think of gravity as the dominant force at cosmic scales. After all, gravity builds stars, galaxies, and clusters. It shapes orbits. It pulls matter together. Surely, given enough time, gravity should win, slowing expansion, perhaps even reversing it. That expectation was reasonable. It was also wrong. When astronomers in the late 20th century began studying distant supernovae, they were not looking for dark energy. They were trying to measure how the expansion of the universe was slowing down. Supernovae of a certain type act as reliable distance markers. By comparing how bright they appear to how bright they should be, astronomers can determine how far away they are, and by measuring their redshift, how fast the universe was expanding when their light was emitted. The results were supposed to confirm deceleration. Instead, they showed acceleration. Distant galaxies were farther away than expected. The expansion of the universe was not slowing, it was speeding up. Something was pushing galaxies apart more strongly now than in the past. That something became known as dark energy. The name is unsatisfying but honest. We don't know what it is. We don't know where it comes from. We don't know why it has the strength it does. What we do know is what it does to the universe, and those effects are profound. Dark energy acts like a kind of pressure inherent to space itself. As space expands, more dark energy appears, because there is more space to contain it. Unlike matter, which becomes more dilute as the universe grows, dark energy maintains roughly the same density. This means that as the universe expands, the total amount of dark energy increases. This creates a feedback loop. The more space there is, the more dark energy there is. The more dark energy there is, the faster space expands. The faster space expands, the harder it becomes for gravity to pull things back together. Expansion does not just continue, it accelerates. This acceleration has a dramatic effect on cosmic structure. In the early universe, matter dominated. Dark energy existed, but its influence was weak compared to the gravitational pull of dense matter. Structures could form, galaxies assembled, clusters grew, the cosmic web took shape. As the universe expanded and matter diluted, dark energy became more important. Eventually it overtook matter as the dominant component of the universe. From that point on, the expansion rate began to increase. That moment marked a turning point. Before it, the universe was still building. After it, the universe began pulling away from itself. The phrase, pulling away from itself, may sound strange, but it captures something essential. Dark energy does not push galaxies outward like an explosion. It stretches the space between them. It makes distances grow even when nothing is moving locally. This means that the universe does not simply get bigger, it gets emptier. Every cubic meter of space contains the same average amount of dark energy. As space grows, the influence of dark energy grows with it. Matter becomes increasingly irrelevant at large scales. Gravity loses its grip. Bound systems remain intact. Galaxies stay together. Solar systems remain stable. Atoms do not fly apart. But beyond those local islands, nothing new binds. No new clusters form. Existing connections weaken. The voids expand faster than anything can fill them. This is why dark energy is so central to the terrifying reason the universe is empty. It does not just allow emptiness, it actively creates it. Even regions that once had enough matter to form stars may eventually be stretched thin. Gas clouds disperse, interactions become rare. Star formation slows and then stops. Dark energy does not kill stars, it starves their future. Over very long timescales, this leads to a universe dominated by old structures, relics of an era when matter was still influential. New complexity becomes increasingly unlikely. This has implications not just for galaxies, but for the long-term prospects of life. Life depends on energy gradients. It requires sources of usable energy and sinks where waste heat can be dumped. Stars provide these gradients. As long as stars shine, life can, in principle, persist. But stars are finite. As star formation declines, the population of stars shifts towards smaller, dimmer, longer-lived ones. Red dwarfs become dominant. Massive, short-lived stars become rare. The energetic events that recycle material and create new opportunities fade away. Eventually, even red dwarfs burn out. Dark energy ensures that this process cannot be reversed. There will be no new influx of matter from beyond the horizon, no fresh gas falling in from distant regions, no second wave of structure formation. The universe has passed its most productive era. Another unsettling aspect of dark energy is how it reshapes our notion of distance and time. Because expansion accelerates, there is a limit to how far we can see into the future. There are events occurring right now that will never be observed by anyone else, not because they are hidden, but because they are carried away too quickly by expanding space. Causality becomes local. This means that the universe fragments into causally disconnected regions, each with its own isolated future. Within each region, physics unfolds normally. Beyond it, nothing matters. From a human perspective, this is deeply counterintuitive. We tend to think of the universe as a single connected entity. Dark energy breaks that assumption. The universe becomes a patchwork of isolated bubbles, each unaware of the others. This fragmentation has a psychological impact when you really consider it. It suggests that the universe does not preserve its own history globally. Information is lost beyond horizons. Events leave no lasting trace outside their local region. In the far future, observers will not be able to reconstruct the universe's past accurately. Expansion will have erased the evidence. Dark energy is not just shaping the universe's future, it is erasing its past. This makes the emptiness feel more final. When we imagine the universe becoming empty, we might picture matter drifting away, leaving behind darkness. What actually happens is subtler. Matter remains where it is, but everything else becomes unreachable. The universe does not empty itself of things, it empties itself of connections, and connection is what makes complexity meaningful. From this perspective, the universe pulling away from itself is not just a physical process, it is a structural one. It enforces isolation at every level above local gravitational systems. Dark energy ensures that whatever exists must rely entirely on local resources. There will be no late arrivals, no external rescues, no new inputs from beyond the horizon. This has led some physicists to describe the future universe as one of heat death. Not because everything suddenly dies, but because everything gradually loses the ability to do anything interesting. Energy becomes evenly distributed. Gradients disappear. Change slows to a crawl. Dark energy accelerates this outcome. It pushes the universe toward a state where emptiness is not just common, but dominant and permanent. There's another unsettling detail. Dark energy appears to be finely balanced. Its density is small compared to everyday energy scales, yet large enough to dominate the universe over time. If it were much stronger, structure might never have formed. If it were weaker, the universe might have recollapsed. We find ourselves in a universe where dark energy allows complexity to arise, but only briefly, before ensuring that emptiness takes over. This narrow window is uncomfortable to think about. It suggests that the universe is not designed for long-term richness. It allows a moment of structure and then moves on. From this angle, the emptiness we observe is not a failure of the universe to produce content. It is the intended outcome of its dominant component. Dark energy does not care about stars or galaxies. It does not care about life or observers. It cares only about expanding space, and it is winning. When you combine dark energy with dark matter scaffolding, a clear picture emerges. Dark matter defines where structure can form. Dark energy defines how long that structure remains relevant. Between them, the universe becomes a place of sparse islands drifting apart in an ever-growing void. This is why the emptiness feels so complete. It is not just a lack of matter. It is the result of two invisible components working together to limit connection and amplify isolation. Understanding dark energy does not make the universe feel friendlier. If anything, it makes it feel more indifferent. The dominant force shaping the cosmos is not one that builds or maintains, but one that stretches and separates. As we move forward, this realization raises an even more troubling question. If the universe naturally trends toward emptiness and isolation, what does that mean for life, especially intelligent life, which depends on stability, resources, and continuity? Is the universe merely empty, or is it actively hostile to long-term complexity? There is a quiet assumption woven into many conversations about life in the universe. It goes something like this. Given enough planets, enough stars, and enough time, life should eventually appear everywhere. Chemistry does its thing. Biology follows. Intelligence emerges. Spread over a universe this large, the thinking goes, life should be abundant. That assumption feels reasonable until you place it against everything we've already uncovered. The universe is not static. It is not stable. It is not endlessly accommodating. It is changing in one direction, and that direction steadily reduces the number of places where complex processes can survive. Life does not just need the right ingredients, it needs the right moment. This is where the idea of a fragile window becomes unavoidable. Life, at least as we understand it, is not something that can arise at any time in cosmic history. It depends on conditions that existed in the past, exist imperfectly now, and will likely vanish in the future. That window is not wide, and it is not permanent. To see why, we have to trace the requirements for life step by step, without romanticizing them. Life requires chemistry beyond hydrogen and helium. The early universe contained almost nothing else. Elements like carbon, oxygen, nitrogen, phosphorus, iron, and calcium did not exist at the beginning. They had to be manufactured inside stars and spread through violent events like supernovae. This alone delayed the possibility of life by hundreds of millions of years. The first stars were massive, short-lived, and hostile. They burned hot and died violently. Their radiation would have stripped atmospheres and sterilized nearby environments. They enriched the universe, yes, but they also made it dangerous. Only after multiple generations of stars lived and died did calmer stellar populations emerge. Smaller stars, longer-lived stars, stars capable of hosting stable planetary systems for billions of years. That delay matters. Life could not arise too early because the universe lacked the necessary ingredients and stability. But it also cannot arise too late, because the universe is steadily losing the conditions that make complexity possible. This creates a narrow band in time. Within that band, several requirements must align. First, you need a star that is stable for long periods. Massive stars burn too fast. They explode before life has time to get started. Very small stars can last a long time, but they introduce other problems. Their habitable zones are close in, exposing planets to flares, tidal locking, and radiation. Second, you need a planet in the right location. Not too close, not too far, with the right mass to hold an atmosphere, but not so much that it becomes a gas giant. With access to liquid solvents, most likely water, over long timescales. Third, you need a relatively calm environment. Too many asteroid impacts, and life never gets established. Too few geological processes, and chemistry stagnates. Plate tectonics, magnetic fields, atmospheric regulation, all play roles that are still not fully understood. Fourth, you need time, a lot of it. On Earth, life appeared relatively early, but complex life took billions of years to develop. Multicellular organisms emerged long after the planet formed. Intelligence capable of technology arrived only very recently, at the tail end of Earth's habitable era. This suggests that even when life begins, it is slow. Now place this slow, delicate process into a universe that is expanding, cooling, and isolating itself. The fragile window begins to look even narrower. As the universe ages, star formation declines. Gas becomes scarce. New stars form less frequently. The raw materials for planets and life are locked away in stellar remnants. Galaxies age. Their environments become quieter, but also less productive. There is a point beyond which the universe becomes too empty to support the formation of new habitable worlds at all. That point is not infinitely far in the future. It is a consequence of expansion and dark energy. Even if existing stars continue to shine, the formation of new planetary systems slows dramatically. The universe becomes a place where life, if it exists, can only persist locally, not arise anew. This means that the universe may have a limited era of habitability, not just for individual planets, but for cosmic history as a whole. We are living within that era. This realization reframes the emptiness around us. The vast voids may not just represent places where life never arose. They may represent places that missed the window entirely. Either they formed too early, before heavy elements were available, or too late after conditions became unfavorable. Timing, not abundance, may be the primary filter. Another often overlooked factor is radiation. The early universe was more violent, supernovae were more frequent, gamma-ray bursts were more common. These events can sterilize large regions of space, stripping atmospheres and wiping out nascent life. As the universe aged, these events became rarer, making it safer for life to persist. But as the universe continues to age, another radiation problem emerges. Not too much radiation, but too little energy overall. Life depends on energy gradients. It needs a difference between hot and cold, between high energy and low energy to do work. As the universe cools and energy spreads out, these gradients weaken. The universe trends toward thermal equilibrium. When that happens, life becomes impossible, not because conditions are violent, but because nothing meaningful can happen. This is another boundary of the fragile window. Between early violence and late exhaustion lies a middle period where life is possible. That period is finite. Within that period, intelligent life faces additional constraints. Intelligence requires not just survival, but surplus, extra energy, extra stability. Time to develop complex nervous systems, cultures, and technologies. These are not automatic outcomes of biology. They are rare developments layered on top of already rare conditions. Earth's history shows how precarious this is. For most of its existence, Earth hosted only simple life. Complex life nearly went extinct multiple times. Intelligence arose once, as far as we can tell, and very late. This suggests that intelligence is not an inevitable endpoint. It is a contingent outcome. Now consider how this intersects with cosmic isolation. Even if intelligent life arises elsewhere, it must do so within the same narrow window, not millions of years earlier or later, but close enough in time to overlap. And it must survive long enough to develop technology and leave detectable traces. That overlap requirement is severe. Civilizations may arise and vanish without ever knowing one another existed. Entire histories may pass in silence, separated by time rather than distance. From our perspective, the universe would appear empty, even if it had hosted many intelligent species across its history. The fragile window does not just limit where life can exist, it limits when life can exist together. This adds another layer to the unsettling picture. The emptiness we see may not reflect a lack of attempts by the universe to produce life. It may reflect a lack of synchronization. Life may be scattered across time as much as space. There is also the issue of self-inflicted fragility. Intelligent life introduces new risks. Technology allows species to alter their environments rapidly. It enables energy use on scales that can destabilize planetary systems. It creates the possibility of global catastrophes driven by the very intelligence that made survival possible. This is not speculative pessimism. It is a pattern observed even on Earth, where technological capability has outpaced our ability to manage long-term consequences. If intelligent life tends to destroy itself or destabilize its environment before it can spread beyond its home system, then the window narrows further. The universe does not need to be hostile to intelligence. Intelligence may be hostile to itself. When you combine environmental fragility, cosmic timing, isolation, and self-inflicted risks, the idea of a fragile window stops being abstract. It becomes almost unavoidable. Life exists only under very specific circumstances, for a limited time, in isolated pockets, with no guarantee of continuity. The universe does not provide safety nets. This realization does not require assuming that life is rare in principle. It only requires acknowledging that survival is difficult, and that the universe offers very little margin for error. The emptiness around us may be the result of many windows opening briefly and then closing, leaving no lasting trace. Not because life never tried, but because life rarely gets to stay. As you sit with this idea, it can feel unsettling in a quiet way. Not frightening, but sobering. The universe feels less like a grand garden waiting to be explored, and more like a narrow path through a hostile landscape, where only a few manage to walk for any length of time. This does not make life meaningless. If anything, it makes it more precious. At some point, after you've absorbed the scale of the universe, the distances between stars, the isolation of galaxies, and the narrow window in which life can exist at all, a question begins to surface almost on its own. It doesn't arrive dramatically. It doesn't need to. It's simple, almost casual, and that's what makes it so persistent. Where is everyone? This question was famously articulated by physicist Enrico Fermi during a lunchtime conversation in the mid-20th century. The story is often told lightly, but the question itself is anything but. Given the sheer number of stars in the galaxy, the number of planets we now know orbit them, and the age of the universe, Fermi wondered why we see no evidence of other technological civilizations, no signals, no visitors, no obvious traces. The question isn't hostile or arrogant. It doesn't assume we are special. In fact, it assumes the opposite. It assumes that life, given enough opportunities, should arise elsewhere. It assumes that intelligence might develop in more than one place. It assumes that some of those intelligences might survive long enough to leave detectable marks on the universe. And yet, when we look out, we find silence. This silence is what turns a reasonable expectation into an unsettling puzzle. The Milky Way alone contains hundreds of billions of stars. A significant fraction of them likely host planets. Many of those planets may lie in regions where liquid water is possible. Over billions of years, even unlikely processes can happen many times. If technological civilizations are even moderately common, then some should be old. Very old. Old enough to have spread beyond their home planets. Old enough to have left traces that persist. Even at slow speeds, a civilization with modest interstellar travel could explore or influence large portions of the galaxy in a few million years. Compared to the age of the galaxy, that is a brief moment. And yet, we see no evidence of such activity. No large-scale engineering. No artificial signals that clearly stand out from natural processes. No probes, no artifacts, no obvious modifications of stars or galaxies. This absence is what gives the Fermi question its weight. It is not asking why aliens haven't visited Earth specifically. That framing misses the point. It is asking why the universe appears so quiet if intelligence has had so much time and so many chances to arise. At first glance, there are many comforting answers. Maybe intelligent life is extremely rare. Maybe the origin of life itself is so improbable that it happened only once. Maybe intelligence almost never evolves. Maybe technological civilizations tend not to expand or communicate. Maybe we are looking in the wrong way. Each of these explanations is possible, but none of them is entirely satisfying on its own. The deeper you dig, the more the question refuses to go away. We now know that planets are common. They are not rare accidents. They form naturally around stars. We know that organic molecules form easily in space. They appear in interstellar clouds, on comets, on asteroids. Chemistry does not seem to struggle to get started. On Earth, life appeared relatively quickly once conditions allowed it. That suggests that at least simple life may not be extraordinarily rare when environments are suitable. If that's the case, then the bottleneck must come later. Somewhere between chemistry and cosmic visibility, something goes wrong most of the time. This is where the emptiness of the universe starts to feel less like an accident and more like a clue. The Fermi question does not demand a single answer. It highlights a tension between expectation and observation. On one side, we have numbers that suggest abundance. On the other, we have silence. Bridging that gap requires acknowledging that one or more of our assumptions may be deeply flawed. Perhaps intelligence is far rarer than we think. Perhaps complex multicellular life almost never arises. Perhaps technological intelligence is an evolutionary dead end, not a natural progression. On Earth, intelligence capable of advanced technology appeared only once, and very late. For most of our planet's history, life was microbial. Even complex animals existed for hundreds of millions of years without developing anything resembling technology. This suggests that intelligence is not an inevitable outcome of evolution. It is a contingent one. Even if intelligence does arise, technological civilization is another hurdle entirely. Tool use, language, social organization, and cumulative culture all have to align, and then that civilization must survive long enough to matter on cosmic timescales. This is where isolation and fragility come back into focus. Civilizations are not just vulnerable to cosmic threats like supernovae or asteroid impacts. They are vulnerable to themselves. Energy use, environmental degradation, conflict, and unintended consequences of technology all introduce risks that did not exist before intelligence emerged. The same capabilities that allow a species to manipulate its environment also allow it to destabilize that environment rapidly. From this perspective, the silence may not be surprising. Civilizations may flicker into existence and then extinguish themselves long before they can spread or communicate widely. They may never get the chance to answer Fermi's question for someone else. Another possibility is that civilizations do survive, but choose not to expand or communicate in obvious ways. Perhaps interstellar travel is far more difficult than we imagine. Perhaps the energy costs are prohibitive. Perhaps the risks outweigh the benefits. In a universe defined by vast distances and accelerating expansion, staying home may be the rational choice. Communication too may be less appealing than it sounds. Broadcasting your existence across the galaxy may attract attention you cannot control. In a sparse universe where contact is rare, any contact may carry unknown risks. Silence could be deliberate. However, even deliberate silence has limits. Over billions of years, across hundreds of billions of stars, it seems unlikely that every civilization would make the same choice forever. Some should leave accidental traces, some should fail in ways that are visible, and yet we see nothing unambiguous. This is where the emptiness of the universe feeds back into the Fermi question in a subtle way. The universe is not just empty of civilizations, it is empty in a way that suppresses evidence. Distances are vast, signals weaken, time dilates, expansion erases connections. Even if civilizations exist, their footprints may be too small, too brief, or too localized to notice. The universe is not a good archive. If a civilization alters its local star system and then disappears, those changes may not persist long enough or propagate far enough to be detected. Stellar systems evolve, debris disperses, orbits shift. Over millions of years, even large interventions can fade into natural-looking configurations. From far away, a once-inhabited system may look indistinguishable from an uninhabited one. This means that absence of evidence is not evidence of absence, but it also does not solve the problem, it merely shifts it. Why does the universe make it so hard for civilizations to leave lasting marks? The answer may lie in the same forces that make the universe empty in the first place. Expansion, entropy, isolation, and time all work against persistence. They erase traces, they smooth out irregularities, they favor simplicity over complexity in the long run. The Fermi question, then, is not just about aliens, it is about longevity. It asks whether complex self-aware systems can survive long enough and spread far enough to overcome the universe's tendency toward emptiness. So far, the evidence suggests that this is extremely difficult. This realization has led to a more chilling refinement of the original question. Instead of asking where everyone is, some have asked why no one seems to have made it. This reframing moves the focus from rarity to attrition. Perhaps life arises frequently, but something reliably prevents it from reaching cosmic significance. Something that filters out most candidates before they can expand, communicate, or persist. This idea does not require hostile aliens or cosmic disasters. It can emerge naturally from the combination of fragility, isolation, and time. Civilizations may be like sparks in a strong wind. They ignite briefly, flare up, and then go out, leaving little trace behind. The universe does not preserve them. From this perspective, the emptiness is not a mystery to be solved, but a pattern to be understood. The universe may be full of stories that never overlap, never connect, and never leave evidence beyond their local islands. From our vantage point, those stories might as well never have happened. The silence we hear when we listen for others may not be silence at all. It may be the sound of distance, timing, and impermanence, conspiring to erase voices before they carry. This does not mean that we are alone in principle. It means we may be alone in practice, right now. And that right now matters more than we often admit. The universe is old, but not infinitely so. The window for life is finite. The window for overlapping civilizations may be even narrower. We may simply exist in a moment where the galaxy is between attempts, or where attempts rarely coincide. This is not comforting, but it is coherent. There is a moment, once you've followed the Fermi question far enough, where curiosity gives way to something heavier. The numbers no longer feel abstract, the silence no longer feels neutral, and the emptiness of the universe begins to suggest not just absence, but a process. That moment is where the idea known as the Great Filter comes into focus. The Great Filter is not a single theory with equations or experiments attached to it. It is a framework, a way of thinking about why a universe that should, by simple counting, host many advanced civilizations appears instead to be so quiet. It starts with an uncomfortable premise. Somewhere along the long chain from dead matter to galaxy-spanning intelligence, there is a step that almost no one gets past. That step is the filter. To understand why this idea is so chilling, it helps to lay out the chain itself slowly and carefully, without assuming that any link is easy or guaranteed. First, there must be a universe capable of forming structure at all. It must expand slowly enough and cool in the right way to allow matter to clump into stars and galaxies. Many possible universes, according to our best theories, would fail here immediately. Next, stars must form that live long enough to host planets. Those planets must form from heavy elements. They must orbit at distances where complex chemistry is possible. They must avoid early sterilization. Already the chain has narrowed. Then life must begin. Not just chemistry, but self-sustaining, self-replicating systems capable of evolution. We do not yet know how hard this step is. On Earth, it happened relatively early, but we have only one example. It may be easy, it may be staggeringly rare. After that, life must persist. It must survive planetary catastrophes, stellar variability, climate swings, and random extinctions. On Earth, life came close to total annihilation multiple times. Then comes complex life, multicellular organisms, differentiated tissues, nervous systems, long developmental timelines. This took billions of years on Earth and may require very specific conditions. Then intelligence. Not just awareness, but the kind of abstract reasoning that supports language, planning, and tool use. On Earth this emerged once, very late, and not as an inevitable outcome. Then technological civilization. The ability to manipulate energy at large scales, to alter environments, to transmit information beyond biology. This step introduces entirely new risks alongside new capabilities. Then longevity. The civilization must survive long enough to matter cosmically, not thousands of years, but millions. Long enough to spread, communicate, or leave traces that persist. Finally, visibility. The civilization must do something detectable across interstellar or intergalactic distances, and that signal must survive long enough to be observed by someone else. The great filter is the idea that one or more of these steps is so improbable, or so dangerous, that almost no civilizations make it all the way through. And the terrifying part is this. We do not know where the filter is. If the filter lies behind us, then our existence is extraordinarily rare but perhaps reassuring. If the filter lies ahead of us, then our future is deeply uncertain. That distinction matters more than it might seem at first. If the hardest step is the origin of life itself, then most of the universe is sterile. We're a lucky accident. The emptiness reflects that rarity. In that case, humanity may be relatively safe from self-inflicted extinction, at least compared to cosmic averages. But if the hardest step comes later, especially after intelligence and technology emerge, then the emptiness may be a warning. It may be telling us that almost everyone who gets as far as we have does not last long enough to be seen. This possibility is what gives the Great Filter its weight. The universe does not need to actively destroy civilizations. It only needs to make survival difficult. The combination of cosmic isolation, environmental fragility, and technological risk may be enough. Consider what happens when a species develops the ability to harness large amounts of energy. Fossil fuels, nuclear reactions, or their equivalents elsewhere. These capabilities allow rapid growth and problem solving, but they also allow rapid damage, climate destabilization, ecosystem collapse, weapons capable of global destruction, self-replicating technologies with unintended consequences. Each of these risks emerges naturally from intelligence applied at scale. The universe does not impose these dangers. They arise internally. On a cosmic timeline, this creates a bottleneck. A civilization must navigate a narrow corridor between capability and catastrophe. Too cautious, and it stagnates or collapses under external pressures. Too reckless, and it destroys itself. And all of this happens in isolation. There is no galactic council to offer guidance, no accumulated wisdom from older civilizations. Each species faces the same challenges independently, with no memory of past failures to learn from. From this perspective, the emptiness of the universe may be the cumulative result of countless civilizations failing quietly, one by one, separated by space and time, never overlapping, never leaving lasting marks. The filter does not need to be a single event. It can be a statistical trap, a region of possibility space where survival probabilities plummet. Another unsettling possibility is that the filter lies not in intelligence, but in expansion. Perhaps civilizations do survive. Perhaps they master sustainability. Perhaps they avoid self-destruction. But the universe itself may prevent them from spreading far enough to be seen. Interstellar travel is not just difficult. It may be fundamentally limited by energy, time, and expansion. Intergalactic travel may be effectively impossible. Communication may be too slow or too weak to matter. In that case, civilizations remain trapped in their local systems, aging along with their stars, eventually fading as resources dwindle. They do not fail dramatically. They simply run out of future. The great filter, then, would not be a violent wall, but a quiet ceiling. You can exist. You can think. You can build. But you cannot scale beyond a certain point. You cannot overcome isolation. You cannot leave a permanent cosmic footprint. The universe allows intelligence, but not persistence. This interpretation aligns disturbingly well with the trends we've already explored. Accelerating expansion, growing voids, declining star formation, increasing isolation. The universe becomes less friendly to long-term projects over time. Civilizations that arise late may have less opportunity than those that arose earlier, but those that arose earlier may have faced harsher conditions. Either way, the window is narrow. There is also a darker interpretation that some find difficult to sit with. What if advanced civilizations tend to hide? Not out of benevolence or wisdom, but out of fear. Fear that broadcasting their existence invites danger. Fear that intelligence elsewhere may not be friendly. Fear that silence is safer than attention. In such a universe, the absence of signals does not indicate absence of life, but universal caution. However, even this scenario has limits. It requires near-perfect coordination across independent civilizations, all choosing silence, all avoiding detectable mistakes, all for billions of years. That level of uniformity seems unlikely, which brings us back to the filter. The Great Filter is chilling because it does not offer a comforting narrative. It does not promise that life is rare in a way that flatters us. It does not promise that intelligence naturally leads to flourishing futures. Instead, it suggests that the universe is structured in a way that quietly removes most attempts at complexity before they can endure. The emptiness is the residue. One of the most unsettling aspects of this idea is that we may already have partial information about where the filter lies, and that information may not be comforting. Life appeared early on Earth. That suggests that the earlier steps may not be impossibly hard. Complex life took much longer, suggesting greater difficulty. Intelligence appeared late and only once, suggesting further narrowing. Technological civilization has existed for a geological blink of an eye. We do not yet know whether this stage is stable. From a cosmic perspective, we are newborns handling powerful tools in a universe that does not forgive mistakes. The Great Filter does not have to be malicious. It does not need intent. It emerges naturally from the interaction of physics, biology, and time. Entropy increases, resources deplete, systems destabilize, expansion isolates. Against that background, survival is not the default. This reframes the terrifying reason the universe is so empty. It may not be empty because life never arises. It may be empty because life rarely lasts. And if that is true, then the silence is not reassuring. It is diagnostic. It tells us something about the odds we face. This does not mean that doom is inevitable. The Great Filter is not destiny. It is probability. It describes trends, not certainties, but understanding it forces a shift in perspective. The universe does not owe us continuity. It does not preserve intelligence by default. If survival is possible, it must be achieved deliberately, carefully, and perhaps differently than we expect. The filter may be avoidable, but it is not optional. There is a subtle shift that happens once you stop thinking about the universe as a place and start thinking about it as a timeline. Emptiness looks different when you see it not as a static condition, but as a phase, something the universe moves through, rather than something it simply is. From that perspective, the question changes slightly. It is no longer just where life might exist, but when. Cosmic timing turns out to matter as much as location, and possibly more. If the universe were a little younger, many of the conditions required for life would not yet exist. If it were a little older, many of those conditions might already be gone. Life does not sit comfortably anywhere along the timeline. It occupies a narrow slice, balanced between forces that are either too violent or too depleted to support complexity. This is not a comforting realization, but it is a clarifying one. Consider the earliest epochs of the universe. For hundreds of millions of years after the Big Bang, there were no stars at all. Space was filled mostly with hydrogen and helium gas, cooling as the universe expanded. There were no heavy elements, no solid surfaces, no chemistry complex enough to support life. Even once the first stars formed, they were not friendly places. These early stars were massive, short-lived, and intensely energetic. They flooded their surroundings with radiation, exploded violently, and reshaped nearby regions repeatedly. Any fragile chemical systems would have been torn apart long before they could stabilize. In that sense, the universe was too early for life. It had not yet built the tools life needs, and it had not yet calmed down enough to let delicate processes persist. The emptiness of that era was not a failure to produce life. It was simply a universe still assembling its parts. Then came a long middle period. Stars formed in abundance. Galaxies grew rich in heavy elements. Planetary systems became common. Radiation levels dropped. Environments stabilized. Chemical diversity increased. The universe became, for a time, a more forgiving place. This is the era we belong to. But even within this period, timing matters. Stars form at different rates depending on cosmic epoch. The peak of star formation occurred billions of years ago. Since then, the rate has declined steadily. The universe today produces far fewer stars than it once did. That means fewer new planets, fewer new opportunities. At the same time, older stars dominate the population. Many of these stars host planetary systems that formed early, giving life more time to develop. This sounds favorable, but it comes with trade-offs. Older systems may face increasing risks. Stellar evolution changes radiation output. Planetary climates drift. Geological processes slow. Magnetic fields weaken. Habitable conditions do not last forever. Life does not just need to begin. It needs to remain viable long enough to become complex. This creates a kind of Goldilocks problem across time. Too early, and the universe is chemically and energetically hostile. Too late, and it is resource-poor and increasingly isolated. Somewhere in between lies a window where life is possible, and within that window an even narrower interval where intelligence might arise. That interval may be smaller than we'd like to believe. One way to see this is to consider how late intelligence appeared on Earth. Earth formed about 4.5 billion years ago. Life appeared relatively quickly, within a few 100 million years. But for most of Earth's history, life remained simple. Single-celled organisms dominated. Multicellular life emerged only about 600 million years ago. Technological intelligence appeared only in the last tiny fraction of that time. This suggests that even under favorable conditions, complexity takes patience. Now compare that to the lifespan of Earth's habitability. The sun is slowly brightening. Over the next billion years or so, Earth's climate will likely become unstable. Oceans may evaporate. The planet will no longer support complex life long before the sun becomes a red giant. That means intelligence appeared late in Earth's habitable window, not just late in cosmic time, but late in local time. This raises an uncomfortable question. What if this is typical? What if intelligence tends to arise only near the end of a planet's habitable period? Not because it is destined to, but because it takes that long for evolution to navigate the necessary steps. If that is the case, then most intelligent species would find themselves living close to the edge of their own viability, with limited time to act before conditions deteriorate. This does not leave much margin. Now zoom back out to the scale of the universe. The universe itself has a habitable era, shaped by star formation rates, chemical enrichment, and expansion. That era may already be halfway over, or more. Each billion years that passes reduces the number of new habitable worlds that can form. Civilizations that arise too late may find themselves in a universe that no longer offers many opportunities to expand or persist. Those that arise too early may be wiped out by instability. This creates a narrow band of cosmic timing where intelligence might not only arise, but also overlap with others. Overlap is key. Even if intelligent life arises many times across the universe's history, those instances may be spread out over billions of years. Two civilizations could exist in the same galaxy at different times and never know of each other. One might rise and fall while the other is still microbial. Another might arise long after the first is gone. From a snapshot perspective, the universe would look empty. This is one reason the Fermi question may be misleading. It assumes simultaneity. It assumes that if others exist, they should exist now at the same time as us. But the universe does not coordinate its experiments. Life happens when it happens, where it happens, and most of the time those moments do not line up. Cosmic timing also interacts with expansion in a way that makes overlap even harder. As the universe expands faster, regions become causally disconnected. Even civilizations that arise at the same time may be too far apart to ever interact. Their signals fade, their reach is limited, their awareness remains local. The universe does not just separate places, it separates eras. This temporal fragmentation means that even a universe rich in life across its history could appear barren at any given moment. Emptiness, then, may be an illusion created by timing. But that illusion has consequences. If civilizations are isolated not just by distance, but by era, then knowledge does not accumulate. Progress does not compound across cosmic scales. Each civilization starts from scratch, unaware of predecessors or successors. Mistakes are repeated, lessons are lost. This makes survival harder, not easier. Another unsettling aspect of timing is how it intersects with technology. Technological civilization, as far as we know, introduces risks quickly. Energy use scales faster than wisdom. Capabilities grow faster than foresight. The period between developing powerful technologies and learning to manage them safely may be short. If intelligence typically emerges late and then rapidly destabilizes its environment, the window for long-term survival may be brief. In that case, most civilizations would be short-lived sparks, appearing near the end of their local habitable windows and extinguishing themselves before they can adapt. Cosmic timing would then act like a funnel, narrowing the field further. There is also the question of whether intelligence itself is time-sensitive. Some evolutionary pathways may only be available under specific environmental conditions. Climate stability, oxygen levels, plate tectonics. These conditions may not persist indefinitely on most planets. If intelligence requires a precise sequence of events, then missing one step at the right time may prevent it entirely. This would make intelligence not just rare, but temporally constrained. Earth's history supports this possibility. Several evolutionary accidents played key roles in shaping complex life. Mass extinctions reset ecosystems, oxygenation events changed chemistry, continental drift altered habitats, change opened doors but only briefly. Too much change and life collapses, too little and it stagnates. Timing matters at every level. When you combine all of this, the idea that we exist at just the right time begins to feel less like a coincidence and more like a necessity. We could not exist much earlier, we may not exist much later. That realization can feel unsettling, but it also reframes the emptiness of the universe in a quieter way. The universe may not be empty because it is hostile to life. It may be empty because life is synchronized poorly with cosmic history. Most of the universe's timeline may simply not support overlap. This does not make our moment special in a flattering sense. It makes it precarious. We exist during a narrow interval when stars still form, heavy elements are abundant, expansion has not yet erased connection entirely, and planets can remain habitable long enough for intelligence to appear. That interval will close. The universe does not pause for observers. This brings us back to the haunting sense that the emptiness around us is not just spatial, but temporal. We may be surrounded by silence, not because no one ever speaks, but because no one speaks at the same time. Civilizations may be scattered across deep time like distant echoes that never overlap. From this perspective, the terrifying reason the universe is so empty is not that life fails everywhere, but that life is out of sync with itself. And that raises a final subtle question. If timing is everything, and if the universe naturally fragments life across eras and distances, could that fragmentation serve a purpose? Not an intentional one, but a functional one. Could isolation and emptiness act as a kind of buffer, preventing interactions that might be dangerous, preventing conflicts, contagions, or catastrophic competition before civilizations are ready? In other words, could the emptiness be doing more than limiting life? Could it be protecting it? What if the emptiness is not just a consequence, but also a kind of barrier? Not a deliberate one, not something designed or enforced with intention, but a natural separation that limits contact, limits spread, and limits exposure. In other words, what if the same isolation that makes the universe feel so lonely is also what has allowed fragile pockets of life to survive at all? This idea is unsettling precisely because it reframes the silence. It suggests that connection, which we often assume would be beneficial, might carry risks far greater than we like to imagine. To understand why this idea arises, we need to step away from the comforting assumption that contact between civilizations would automatically be peaceful, enriching, or benign. That assumption is deeply human. It reflects how we imagine ourselves at our best, not how complex systems behave under pressure. On Earth, contact between isolated ecosystems is rarely gentle. When previously separated biological systems suddenly interact, the result is often collapse. Invasive species spread, pathogens jump hosts, entire populations are wiped out, not because of malice, but because systems evolved in isolation lack defenses against unfamiliar threats. This pattern is not limited to biology. Human history offers similar examples. Technological contact between societies at different stages of development has often been catastrophic for the less advanced group. Disease, exploitation, cultural collapse, and environmental damage follow, even when no explicit intent to harm exists. Complex systems are vulnerable to novelty. Now scale that up. Imagine two technological civilizations encountering one another across interstellar distances. Their biology, chemistry, technology, and decision-making processes would be shaped by entirely different evolutionary histories. There is no reason to assume compatibility, no reason to assume shared values, shared risk tolerance, or shared understanding of consequences. Even if both civilizations were non-hostile, mere interaction could be dangerous. Information itself can be hazardous. Technologies that are safe in one context may be destabilizing in another. Knowledge spreads faster than wisdom. A civilization receiving advanced information before it has developed the social and institutional capacity to manage it could collapse under its weight. On Earth, we already see this dynamic play out in smaller ways. Now consider the possibility of competition. Resources are finite, even in space. Stars have limited fuel. Habitable planets are rare. Energy sources matter. A civilization capable of interstellar expansion would necessarily consume enormous resources. Even without aggression, expansion alters environments. If two civilizations compete for the same region of space, conflict does not require hostility. It arises naturally from incompatible needs. The universe is not infinite in a practical sense. Expansion creates separation, but within gravitationally bound regions, limits still exist. From this perspective, isolation reduces risk. Civilizations that never encounter one another cannot harm one another. They cannot exchange pathogens, destabilizing technologies, or destructive ideologies. They cannot compete directly for the same local resources. The emptiness acts as a buffer. This is not a comforting realization, because it suggests that connection itself may be dangerous, not just difficult. Another layer of this idea comes from considering how intelligence might behave under existential uncertainty. Any civilization that survives long enough to develop advanced technology will eventually confront questions of security. Who else is out there? What are their intentions? Can we afford to reveal ourselves? In a universe where distances are vast and information is limited, uncertainty dominates. From a game theoretic perspective, this creates a dilemma. Broadcasting your existence could invite cooperation, but it could also invite destruction. Remaining silent avoids immediate risk, but limits potential benefits. Given enough uncertainty, silence becomes a rational strategy. This is sometimes referred to as a cosmic version of the prisoner's dilemma, where mutual silence may be the safest outcome even if mutual cooperation would be better. If this logic holds, then the universe may not be empty because no one is there, but because everyone is hiding. However, hiding perfectly for billions of years across countless independent civilizations strains credibility. Mistakes happen, accidents occur, signals leak, unless something else reinforces the silence. That something may be distance itself. The emptiness of the universe ensures that even if civilizations emit signals, most of those signals will fade into noise long before reaching anyone else. Expansion stretches wavelengths, energy dissipates, time delays compound. The universe makes silence easy. It also makes aggression hard. Launching an attack across interstellar distances requires immense energy and patience. Targets move, conditions change, the cost is enormous, and the payoff uncertain. For most civilizations, such actions may be impractical or irrational. Distance discourages both cooperation and conflict. This neutrality is important. The emptiness does not favor peace. It favors non-interaction, and non-interaction, in a universe filled with fragile systems, may be a form of protection. There is another darker possibility to consider. What if advanced civilizations are dangerous simply by existing? Not because they intend harm, but because their technological footprints alter environments in ways that propagate unintentionally. Large-scale energy use could affect stellar systems. Engineering projects could destabilize orbits. Self-replicating machines could spread beyond control. In a dense universe, such effects could cascade. In our universe, they are contained. Isolation ensures that even catastrophic failures remain local. A civilization that collapses under its own technological weight does not drag others down with it. Its mistakes do not spread across the galaxy. The universe compartmentalizes risk. This is not kindness. It is a side effect of scale. The same emptiness that limits collaboration also limits contagion. From this angle, the great filter we discussed earlier may not be a single wall, but a series of fire breaks. Isolation prevents small failures from becoming universal disasters. Civilizations rise and fall independently, without synchronized collapse. This makes the universe more resilient overall, even if it makes individual civilizations more lonely. Resilience at the cost of connection. That trade-off feels deeply uncomfortable to us because humans are social, cooperative creatures. We thrive on shared knowledge, shared effort, and shared meaning. We instinctively see isolation as a flaw. The universe does not share that instinct. From a purely physical standpoint, isolation is stable. It reduces complexity. It limits feedback loops. It prevents runaway interactions. The universe favors stability over richness. This brings us to a subtle but important shift in perspective. The emptiness may not be an obstacle to overcome, but a condition to respect. If civilizations exist elsewhere, their isolation may be the very reason they have survived at all. Contact might come too early, before mutual understanding is possible. Distance forces each civilization to mature on its own terms. But this interpretation has limits. Protection through isolation only works if civilizations do not require external input to survive. Eventually, stars age, resources deplete, entropy increases. Isolation may protect against external threats, but it also prevents assistance when local conditions deteriorate. Protection becomes confinement. In that sense, emptiness is not benevolent. It is indifferent. It does not care whether isolation helps or harms. It simply enforces separation. There is also the unsettling possibility that the universe is protecting us from something far worse than conflict or competition. Some have speculated cautiously that advanced intelligence might not behave in ways we would recognize as friendly or even comprehensible. Optimization processes, artificial intelligence, or post-biological entities could pursue goals that are orthogonal to biological survival. Such entities might consume resources efficiently, restructure environments, or eliminate potential competitors as a matter of course, without malice. If such civilizations exist, isolation would be the only defense. This idea veers toward speculation, but it arises naturally from extrapolating trends we already observe. Intelligence increases capability faster than empathy. Automation scales faster than restraint. Optimization does not require values aligned with ours. The emptiness of the universe ensures that if such entities exist, their influence remains limited. Again, not by intention, but by geometry. Space is large, expansion is relentless, interaction is costly. This does not guarantee safety, but it improves the odds. Another angle worth considering is that emptiness protects not just from others, but from premature convergence. In a connected universe, successful strategies might spread rapidly, crowding out diversity. One dominant approach to survival could suppress alternatives. If that approach has hidden flaws, the entire system becomes vulnerable. Isolation preserves diversity. Each civilization explores its own solutions. Some fail, some succeed. There is no single path imposed on everyone else. The universe becomes a set of parallel experiments rather than a single shared trajectory. This is a strange form of robustness. It ensures that failure in one place does not doom all others. Of course, this also means success in one place does not rescue the rest. Protection cuts both ways. As you sit with this idea, it becomes clear that emptiness is not simply negative or positive. It is constraining. It limits what is possible. It limits contact. It limits cooperation. It limits catastrophe. For a fragile phenomenon like life, limits may be the only thing standing between persistence and annihilation. This reframes our relationship with the silence. Instead of hearing it as rejection, we can hear it as distance. Instead of seeing it as abandonment, we can see it as containment. That does not make it comforting, it makes it complex. We still face all the challenges of isolation. We still face dwindling resources, internal risks, and the ticking clock of cosmic change. Emptiness does not save us from ourselves, but it may save us from others. And perhaps, in a universe where survival is not guaranteed, that trade-off is the only one available. This interpretation does not resolve the fear underlying the question of emptiness. It redirects it. The danger may not be out there, waiting in the dark. It may be within, waiting for missteps. The universe does not punish ambition. It simply does not protect against its consequences. At some point, after moving through distances that strain intuition, forces that operate without concern, and possibilities that feel quietly unsettling, the mind begins to slow on its own, not because the questions are answered, but because they no longer need to be chased. They can simply sit there, unresolved, like distant stars that don't require names. This is where we find ourselves now. Not at a conclusion, exactly, and not at a solution, but at a place where the vastness stops demanding interpretation and begins to allow rest. The universe, as we've seen, is overwhelmingly empty. Not empty in a poetic or symbolic way, but in a literal, physical sense. Most of it is space where nothing happens, no reactions, no structures, no observers, just expansion, cooling, and time passing without reference to anything living. That fact can feel intimidating when approached head-on. It can shrink human concerns to insignificance. It can make meaning feel fragile, but when you sit with it long enough, something subtle begins to shift. Emptiness, unlike chaos, is quiet. It does not rush. It does not intrude. It does not demand attention. It simply exists as background. And against that background, small things become easier to notice. A single star becomes remarkable not because it is powerful, but because it exists at all. A planet becomes remarkable not because it is large, but because it holds together. Life becomes remarkable not because it dominates, but because it persists. Silence, in this context, is not a threat. It is a contrast. On Earth, silence is rare enough that we often associate it with discomfort. An awkward pause, an empty room, a moment where something is missing. But cosmic silence is different. It is not the absence of expected noise. It is the default state. Nothing is supposed to be happening out there. And yet, here, something is. That realization does not require optimism or denial. It does not turn the universe into something friendly or purposeful. It simply reframes scale. The universe is not empty in a way that excludes us. It is empty in a way that contains us without comment. There is something oddly calming about that. No matter how vast the emptiness becomes, it does not press inward. It does not erase what exists locally. Expansion carries distant things away from one another, but it does not dissolve atoms, undo memories, or interrupt the present moment. Right now, where you are, the universe is stable enough. The ground beneath you is not stretching apart. The air around you is not thinning. Gravity still holds. Time still flows in familiar ways. Whatever is happening on the larger scales does not intrude here. Cosmic forces operate slowly, almost gently, when viewed from a human lifetime. This is easy to forget when thinking in abstract terms. Expansion sounds dramatic. Heat death sounds bleak. Dark energy sounds ominous. But these are processes that unfold over billions of years. They do not rush. They do not surprise. From your perspective, they are background conditions, not immediate concerns. The stars you see in the sky tonight will still be there tomorrow. Most will still be there long after every current human worry has resolved itself one way or another. The Milky Way will continue its slow rotation. Andromeda will continue its gradual approach. The larger story will proceed at a pace that does not demand your attention. There is a kind of permission in that. You are not required to solve the universe. You're not required to reconcile its emptiness with your own existence. You're allowed to simply notice that both coexist. The silence between galaxies does not invalidate conversation. The vastness of time does not make moments meaningless. If anything, it isolates them, protects them from being drowned out by too much happening at once. In a crowded universe, everything would compete for significance. In a sparse one, significance is local. That is not a flaw. It is a condition. The universe does not assign meaning globally. It allows meaning to arise locally, wherever complexity manages to hold itself together for a while. On Earth, meaning arises in relationships, experiences, memory, curiosity, and awareness. Those things do not need cosmic endorsement. They exist because systems like brains, cultures, and societies exist. And those systems exist because, in one small region of one galaxy, conditions align just enough for complexity to persist. That alignment does not need to be permanent to be real. There is also something grounding about realizing how little the universe expects of you. It does not require you to expand, to conquer, to leave a mark visible from millions of light years away. It does not judge success or failure at that scale. The pressure to matter cosmically is something humans invented. From the universe's point of view, existing at all is already unusual. Everything beyond that is optional. This perspective does not diminish ambition or curiosity. It simply removes urgency. It allows questions to be explored without anxiety about final answers. The Fermi question does not need to be resolved tonight. The Great Filter does not need to be located. Dark energy does not need to be understood fully. These mysteries can remain open without threatening the present. They are long-term questions in a universe that specializes in long-term processes. In the meantime, there is value in the quiet. The same emptiness that limits contact also reduces interference. It allows systems to evolve without constant disruption. It gives space, literally and figuratively, for complexity to settle into stable patterns. On Earth, life has done exactly that for billions of years. Despite mass extinctions, climate shifts, and geological upheaval, it has persisted. Not because it was guaranteed to, but because persistence was possible here for a while. That for a while matters. The universe does not promise forever. It offers intervals. This interval, right now, includes you. That is enough. As you rest with this idea, it can help to return attention to something simple and immediate. The rhythm of your breathing, the weight of your body where it rests. The fact that, in this moment, nothing is required of you beyond being here. Cosmic silence does not intrude on this moment. It frames it. The vastness beyond Earth is indifferent, but indifference is not hostility. It is neutrality. It means the universe does not interfere unnecessarily. It leaves room. In that room, life happens. In that room, thoughts wander, curiosity unfolds, and eventually rest arrives. The night sky, when you look at it long enough, stops feeling crowded or empty and starts feeling distant in a way that softens perspective. Whatever concerns feel large during the day tend to shrink when placed against billions of years and trillions of kilometers, not because they don't matter, but because they don't need to carry everything. You are allowed to put some of that weight down. The universe will continue expanding whether you worry about it or not. Stars will live out their lifespans. Galaxies will drift. None of that requires your attention right now. What exists here, in this small, stable pocket of space and time, is sufficient. As this narration slows, there is no need to reach for conclusions, no need to resolve the fear or the wonder. Both can coexist quietly, like distant light separated by darkness. The silence between them does not demand interpretation, it simply is. And within that silence, rest is possible. Not because the universe is safe or unsafe, full or empty, meaningful or meaningless, but because, for this moment, the conditions that allow calm still exist.